Here is our differential equation with initial condition x at time 0 equal to 10. If we take the right-hand side and define a function given by the right-hand side, call it f, then we can plot f, and when we plot f, what we will find out is that the equilibrium value for x is going to be 1.5, which of course we expected because 3 divided by 2 is 1.5. What this plot does not tell us is how long it takes to get to that equilibrium time. So let's try to solve the equation. If we do that, we end up with a complicated formula involving the product log. Now, the product log is a Mathematica function which, for a given complex number z, tells us the value of w, for which w times e to the w returns z. That's a transcendental function, and I want something more intuitive, and I also want to be able to plot solutions. So let's give up on trying to solve the equation, and for the moment, let's try to forward integrate the equation. Now, in Roman Mader's book on programming in Mathematica, he actually provides code for the Runge-Kutta algorithm. Using that code, I'll set up my variables as t and x, and I'll use a system of two differential equations, but the first one is trivial. It's just dt by dt equals 1, which will give me equally spaced values of the time variable. And then, of course, here's the derivative of x with respect to t. So we'll do it twice. We'll start out with an initial value of 10 for x and 1 for t. We'll compute the result using Runge-Kutta. We'll get a set of points, and this is where I'm using that time business. We'll also do it with an initial value of x at 0.5. In other words, below 1.5 the second time and above 1.5 the first time. And if we show a plot of these two solutions, we get something that's very helpful, because it shows that somewhere around 50 or 60 time units is when we reach equilibrium at 1.5. As you can imagine, a line along here, an asymptote for these two solutions at 1.5. Well, that's all very well, but I would like to see something more comprehensive and also a solution in closed form. My friend Radu Diaconescu suggested, instead of solving for x in terms of t, how about we solve for t in terms of x? In other words, we'll turn the equation upside down. That means taking the reciprocal on the left, so that would give us dt by dx, and on the right, if we want to get the reciprocal of this, we'll use Mathematica or do it in our head and get abx over a minus bx as the reciprocal on the right-hand side. And we set up our solution using dsolve, and we get a nice function here that involves only logarithms. Fine. Let's see if we can plot that for a range of values of the input variable x. So I'll start x at 0.1 and run it out to, I don't know, 64 times 0.1, which is 6.4. And if we do that, let's compute it. We get a couple of little problems at the asymptote. But anyhow, we can plot this answer, and we get a very nice graph. Not nearly as nice as a Mandelbrot set, of course, but it is a picture that shows very, very graphically that any of the initial conditions for x leads to around time 40 or 50 to the asymptotic value of 1.5 right along here. And that's what we wanted to see.